So here we are, we're discussing Earth's interior, plate tectonics, Earth's crust. And what's interesting about geology really becomes the slide that I have right here on the board now, where we've got this picture from 1871, which is right here on our left. And let me circle it because I'm clever that way. 1871 on the left and 1968 on the right. And you'll note that these images are of the same location and they're almost identical. Now, 100 years has gone by. And if I asked you to really take a look at these images and really concentrate on the differences between the two, it would be extremely difficult to find any major differences. Maybe you could look here in the 1871 picture and you'll notice that this little outcrop is a bit smoother here 100 years later. Maybe this is a little bit more defined than it is over here 100 years later, but by and large, everything looks the same. And again, we've got an approximate 100-year separation between the two. If we are living creatures and we live to 70, 80 years or so on average, we're still living less than what we see here when we don't see any changes. And so when we talk about geomorphic processes, the changing of the Earth, it happens pretty slowly, which makes it a relatively challenging science. And so with that in mind, in this particular section, we're going to answer and ask a few questions. Number one, how do landforms evolve? Number two, where do they come from? And then, of course, number three, how rapid are geomorphic processes? And the key words that we'll be talking about in this section are going to be tectonic, weathering, and deposition. Now, to start it all off, there was really, when I say there was, we're going to date ourselves back to a few hundred years. And there are two schools of thought in geology. One school of thought is called catastrophism, and the other school of thought is called uniformitarianism. When we talk about catastrophism, what we're essentially looking at is an Earth that has not changed since its very beginning, except for a few catastrophic events that might have changed the landscape of the planet. As you can well imagine, catastrophism was actually fairly popular, especially in religious circles. As a matter of fact, in the King James Bible, Archbishop James Ussher concluded that the age of the earth was around 6,000 years old from his prediction, i.e., the world started at around 4004 BC. And James Ussher said that the reason we don't see changes today is because the earth itself doesn't change except for some catastrophic events, maybe a periodic volcano, a periodic earthquake, some river and weathering. Maybe that changes the landscape. Now you might say, well, where did 4004 BC come from? And the simple answer is biblical genealogy. So what James Ussher did was he looked at all the generations in Genesis, he went backwards, and he concluded that the world started right at around 4004 BC. It's not a particularly inconceivable idea, especially if you're a fairly religious person, because again, your mindset is the world started with Adam and Eve anyway. Now, with that in mind, the earth is not 6,000 years old. Rather, the Earth is around 4.6 billion, and that's with a B, years old. So now the question becomes, and by the way, the 4.6 billion year old number, you want to question that, right? You want to be asking me, well, how do you know that? And we'll talk about that as well as we proceed. For right now, we note that the oldest rock that we've found on Earth is about 3.9 to 4 billion years old, and we found that right in the center of Australia. So we've got rock on Earth about 4 billion years old. We're missing about 600 to 700 million years of information, and I'll tell you why that's the case soon. But I can also note that this number has been found in relatively old, well, relatively very old solar system rocks that are in the form of meteorites, asteroids, lunar rock, etc. So we do have rock that reaches about 4.5, 4.6 billion years old in our solar system. This leads to another school of thought called uniformitarianism. And with uniformitarianism, let me see if I can erase my screen. There we go. With uniformitarianism, here's the mantra, and I'm going to draw a picture of it. The present, so I'm going to draw a present. The present is the key, and let me draw a key, to the past. And here's my clock. This is really bad, so my apologies. The present is the key to the past. In other words, if you went outside today, and let's say that you went to Cowles Mountain, right outside San Diego State around Mission Valley, and you look at Cowles Mountain, and if your assignment was to go out there every single day and draw a picture of Cowles Mountain, it's going to look the same. Every single day will look the same. I could ask you to do the same exact task for 100 years. Every single day, it'll look the same, geologically speaking. It doesn't mean that the mountain is not changing. It just means that it's changing slowly. That's the present. The present is the key to the past. So biology, chemistry, physics tends to move slowly, especially when we talk about geology. And again, if the Earth is 4.6 billion years old, that's a super long time for change to occur. So therefore, in terms of the rapidity of landform evolution or geomorphic processes, it happens slowly, but over 4.6 billion years, that's a long time for things to change. And so when we look at a place like the Grand Canyon was cut down by the Colorado River. Millions of years for that to take place. If you go to the Grand Canyon every single day from here on out for the rest of your life, it's not going to change that much. You're not going to witness the Grand Canyon getting much bigger, but taking over millions and millions of years, this is the result that we have, the Grand Canyon. So now with uniformitarianism, again, the present is the key to the past. That doesn't mean that there's not catastrophic events. There are. So tattered within uniformitarianism are periodic catastrophic events, volcanoes, earthquakes, landslides, tsunamis, and all of those things are absolutely going to affect landform evolution. So geology really becomes uniformitarianism with tattered bits of catastrophism interwoven throughout history. And that's something to keep in mind whenever you're asking the question of, well, why aren't I seeing changes? They're just changing super slow. Okay, so again, the Earth's surface has been shaped by episodic events over long periods of time. Some of these events may have been catastrophic for the life of our planet, resulting in mass extinctions, i.e. the death of the dinosaurs 65 million years ago, which we can talk about a little bit later on as well. Generally, biological, chemical, and physical processes are relatively slow, but taken over long periods of time, this leads to great changes to the surface of the Earth. And again, this is uniformitarianism. Earth is old, about 4.6 billion years old. And again, we know this from a lot of age dating of rocks. Not to mention that we've got a lot of computer models on the origin of the solar system, and this date works with our viewed and observed rocks that we find and various other elements of solar system evolutionary processes. Okay, so let's take a look at the structure of the planet. This is where we really begin to take a look at geology. The Earth itself is like an onion. I can cut it open. Well, I can't cut it open, but you know what I'm saying. If we were to cut it open, this is what the Earth would look like. There is a core, and the core of the Earth is about 2,100 miles or so in thickness. There is an inner core, which is solid, by the way, solid irons and nickels. And then there is an outer core, and this outer core is liquid. That's really, really odd. And so these are irons and nickels. These are irons and nickels, but it just so happens that we've got a liquid outer core and a solid inner core. Now, if it was the reverse, maybe it would make a little bit more sense because as you know, the hotter something gets, then it's going to melt. I mean, ultimately, you'll reach a melt temperature. And so it's not unreasonable to suggest that if you go in the core is going to be hotter than the outer core because the inner core has more pressure pushing on it. If you came to that conclusion, you would be correct. But there's an ideal gas law, and it's PV equals nRT. And you see this in chemistry quite a bit. And you note the relationship between pressure and temperature. As pressure goes up, then the melt temperature is going to go up as well. And as it so happens, the pressures here in the outer core meet the melt temperature. The inner core, the pressures are super high, but the temperatures have not met the melt temperature. That's why the inner core is solid and the outer core is liquid. Now, a question you might be having right now is how do we know this? And we'll talk about how we know this in just a second. Outside of the core, you have the mantle. The mantle is about 1,800 miles or so in thickness. It is made up predominantly of iron, magnesium, and silicon. You eventually reach the crust, and the crust itself is relatively thin. It's only 3 to 43 miles, with the oceanic crust being 3 to 8 miles or so in thickness. It's iron rich. The rock is basaltic. Continental crust is thicker. It's 20 to 43 miles of thickness. Its primary ingredients are iron, silicon, and aluminum, and it is a granitic type rock. Now, why am I giving you the elements? I'm giving you the elements because the heavier stuff is down here toward the core, and as you go toward the crust, then the elements become lighter in weight. I don't think you can read that. So we'll say here, lighter in weight. And this makes sense because when the Earth formed about 4.6 billion years ago, it was a ball of goo. And over time, during the solidification process, the heavy stuff sank toward the core. The lighter stuff obviously floated toward the surface. And that's exactly what we see in the distribution of heavier elements on our planet. Now, there's another thing that we really need to take a look at. And that other thing is going to be the lithosphere and the asthenosphere. When you take a look at the upper crust, when you take a look at the uppermost part of the upper mantle plus the crust, then you have what's called lithosphere. So again, lithosphere is crust plus the uppermost part of the upper mantle, and it's solid, it's thin, it's brittle. Beneath the lithosphere, you've got the asthenosphere. And the asthenosphere, known as the weak sphere, is a solid, but it's capable of flowing like a liquid. Again, it's solid, but it's capable of flowing like a liquid. I conveniently say that it's plastic-like, even though that's probably not quite the right way to describe it, but it's a solid that's capable of flowing like a liquid. Okay, asthenosphere, lithosphere, both extremely important, and this is where we're going to spend most of our time in a physical geography class. All right, now, how do we know this? This is a 4,000-mile radius picture. How do we know what the interior of the Earth looks like going 4,000 miles deep? Your first inclination is, well, can we dig a hole? And the answer is you can dig a hole, but the deepest you're going to dig is a few miles. I think the deepest hole ever dug on the planet is about 8 miles. Many, many years ago, Russians tried to dig through the crust to the mantle for various reasons, and they couldn't quite make it. The machinery couldn't withstand the enormity of pressures of such a big hole. Now, with that said, 3, 4, 5, 6 miles of information is not shabby. You can get all sorts of information, but again, it's just not a lot. The next thing we can do is something called isostasy. And in isostasy, what you can do is compare the density of one thing relative to the density of another thing. The most obvious example of this is an iceberg. In an iceberg, whenever you see the iceberg, you're looking at 10% of it because 10% of the iceberg is above water, 90% of the iceberg is below water. If I were to shave off the top of the iceberg, you know what the iceberg is going to do? It's going to push upward and it's going to maintain the 10%, 90% ratio. That's because the density of this ice is unique compared to the density of the seawater. And the densities, if they are consistently the same of the ice versus the seawater, you will always maintain that 10 to 90%. And again, no matter what I do to that ice, it's going to always maintain 10 to 90. That is called isostasy. So again, isostasy is really keeping that equilibrium when you've got different components. So let's take a look at the crust, like the continental crust. Here's a big chunk of it in this diagram. There's a certain amount of crust that goes into the mantle, right? Now, whatever I do, if I can cut off a piece of this crust, it's going to lift, and there's going to be a certain amount above the mantle and a certain amount below the mantle. So if we know how much the crust moves or how much of the crust is above mantle versus how much of the crust goes into the mantle, then we can figure out what the density of the crust is relative to the density of the mantle. Now we know by measurement, the density of the continental crust on average is about 2 grams per cubic centimeter. We actually know how deep the continental crust goes into the upper mantle, and therefore we can figure out that the upper mantle has a density of about 3.3 grams per cubic centimeter, which gives us information about what the upper mantle is made of. Okay, so this is great. We've got a few miles from digging a hole. Maybe we have a few hundred miles from looking at isostasy. We got a few thousand more miles to go. And now the question becomes, how do we figure that out? And the answer is going to be this picture right here, some seismology. As a matter of fact, most of our knowledge of Earth's interior comes from the study of P waves and S waves. So you might say, well, what are P waves and S waves? Whenever there is an earthquake, the energy waves emanating from that earthquake are going to emanate predominantly in the form of P waves and S waves. And again, they are energy waves. P waves move like this. They're pushing and they're pulling. S waves move like this. They're much more sinusoidal. So that is the movement of the P wave and the S wave. So again, this is S wave and this is P wave. They are both energy waves emanating from the epicenter of an earthquake. Now, these energy waves will go through the earth, just like this picture here. The S waves and the P waves will go all the way through the earth. And as a matter of fact, what we can do is set up seismographic stations all around the planet. And these seismographic stations will monitor the Earth's movement at all times. And so these are the results of seismographic information being picked up. These are scales, this is Richter scale stuff that we'll talk about much later when we get into our conversation of earthquakes. But just know that right now, there are seismographic stations set up around the entire world. So if an earthquake occurs here, S waves and P waves will go through the earth to all of these seismographic stations around the planet. You will note that if the earthquake is here, opposite to the earthquake, you will have an S wave shadow zone. And the S wave shadow zone will be about 140 degrees to 140 degrees from the earthquake's epicenter. In addition to that, you'll notice that there is a P wave shadow zone here and here, from about 105 degrees to 140 degrees on both sides. Why is it that I have an S wave shadow zone? That is, I can't see any S waves coming through the Earth. All I get are P waves. And right here, here's a P wave shadow zone where I'm not going to get anything, not even P waves. The answer is the following. S waves only travel through solids. P waves travel through solids and liquids. So one of the reasons that we know that the outer core is liquid and we know what the size of the outer core is because there is an S wave shadow zone. If I have an earthquake here, the S wave shadow zone will be over here. If I have an earthquake here, the S wave shadow zone will be over there, and so on and so forth. So we know what the inside of the planet is looking like based in part because of the S wave shadow zone. In addition to that, when a P wave hits the outer core and then eventually the inner core, it'll get bent or refracted. And it gets refracted based upon changing from one medium of a certain density to another medium of a different density. And you can see that here in this diagram, where I've got a laser beam going through air, it hits water, and then it bends. The amount of that bend is going to be dictated by whatever the density of this object is, in this case water, relative to the density of this object, in this case air. So if I have a P wave that starts out and it's going through a medium of density, which I know, and then it bends, then because of this equation here called Snell's law, I can figure out what the density of that other medium actually is. So the P waves coupled with the S waves are going to tell us what the interior of the planet actually looks like. It's fascinating. This is going to give us most of everything that we know about what the interior of the Earth looks like. Now, by the way, there's something else that I haven't really discussed. We also know that the liquid outer core is a liquid outer core because we have a magnetic field. And the magnetic field is due to the fact that we've got a liquid outer core. We won't get into the physics of it just now, but suffice to say, if you want to have a magnetic field, then what you need to have is a moving electric field. And because the liquid outer core is liquid outer core, it promotes a moving electric field, which therefore gives us a magnetic field. So we know we have a liquid outer core because we have a magnetic field. But we also know that we have a liquid outer core because of the S wave shadow zone and the P wave shadow zones. Okay, so this is really key. This is paramount. The inside of the planet, we really understand it to a certain extent because of P waves and S waves, more so than anything else. There's other things too, by the way. Like we know, for example, what the crust density is, and we can also take a look at how Earth orbits the sun, and we can figure out what the total density of the Earth is by knowing the orbital dynamics. And because we know what the crustal density is, we can infer what the inside of the planet density is, and therefore we can infer what the ingredients are, and so on and so forth. So there's a lot of very smart things that we can do to figure out what the inside of the planet looks like. But the most important one is going to be P waves and S waves. All right, so let's move forward. Let's go real basic, super basic. For our purposes, everything that we know of is made of atoms, right? Atoms are made of protons, electrons, and neutrons. These atoms make up elements. And when you look at the periodic table of the elements, there's over 100. And all of these different elements have a differing number of protons, electrons, and neutrons. As a matter of fact, what makes an element really is the number of protons that you find in that particular atom. Hydrogen is number 1, it is 1 proton. Helium is number 2, it's got 2 protons. Carbon is number 6, it's got 6 protons. Oxygen is number 8, it's got 8 protons, and so on and so forth. Now, of these 100 plus elements, you all only need to know these top 8. You need to know oxygen, which is O, silicon, Si, aluminum, Al, iron, Fe, calcium, Ca. I did it like California. Calcium, Ca, sodium, Na, potassium, K, and magnesium, Mg. And the reason why these are important is because these 8 elements make up about 98% of the Earth's crust. I don't need you to know all the elements of the periodic table, but you do need to know the top 8 that make up the Earth's crust. Oxygen, silicon, aluminum, iron, calcium, sodium, potassium, magnesium. Now, these 8 elements combine together to make minerals. Minerals then become the building blocks of rocks. There are over 2,000 mineral groups. The most important mineral group for our purposes is really going to be the quartz group, which is silicon dioxide, right? That's going to be the most important element for us, or most important molecule for us in terms of minerals and rocks. Now, in terms of rocks, there's a bunch of rocks out there. You got your basalts, your granites, your andesites, your sandstone, claystone, siltstone, marble, gneiss, schist. There's more. There's way more. I don't care that you know any of those, but the most important things that you should know is that there are 3 major groupings of rock. There's igneous, sedimentary, and metamorphic. So again, just to summarize, we start with our atoms. The atoms make up the elements. The elements make up the minerals make up the rocks, and the rocks that we really care for are igneous, sedimentary, and metamorphic. You will have rocks that fall under these different categories, so the most important thing to note are the categories of rocks: igneous, sedimentary, metamorphic. Let's take a look at each one of them. So what is an igneous rock? An igneous rock is derived from a melt process. So you're going to get melting of rock in hot, deep crust and upper mantle. Eventually, this molten material will crystallize again. It'll solidify, and that becomes your new rock. So an igneous rock comes from melt. A sedimentary rock is the weathering and erosion of exposed rocks at the surface. And so your exposed rock is going to break down into fine sediment. These sediments can deposit, bury, and lithify. And that lithification process leads to the creation of a new rock. So in this regard, sedimentary rock is due to weather or weathering events. And by the way, weathering events can also include being caught in a river, for example, and flowing that way. It could also be a chemical process. If you've got a thin layer of water, for example, and it's salt water, but then the water evaporates, and then you have rock salt crystallizing out of this solution, that's also a sedimentary rock. The third type of rock is metamorphic rock. And metamorphic rocks are derived from high temperatures and pressures, typically deep inside the Earth's crust and upper mantle, and this is the recrystallization of a rock in a solid state. There is no melt. If it melts, then you've got an igneous rock. So this is extreme heat and pressure. And I really want to be clear with metamorphic rocks. You're going to take an existing rock. You're going to put this existing rock under extreme heat and pressure. And the rock itself is going to recrystallize in the solid state form. It doesn't melt. The molecules inside just rearrange themselves to a certain extent. So when we talk, for example, about diamond, which is a metamorphic mineral, you're taking coal, which is carbon, you're putting it under extreme heat and pressure, you're metamorphosizing that structure, and the internal carbon structure is shifting, and now it's forming diamond. You didn't melt anything. It's just the recrystallization of the rock in a solid state. So these are our 3 types of rock categories: igneous from melt, sedimentary from weathering, metamorphic from extreme heat and pressure. Okay, let's take a look at each one of them. So igneous rock, they form as magma cools and crystallizes. So what's magma? A magma chamber is going to be a chamber of molten rock beneath the Earth's surface. Now, you might be saying, where's this molten rock chamber coming from? And the answer is, we'll talk about that later. Molten material can then go upward within the crust. And it's going upward because it's hot, it's lighter in weight, there's a lot of gases in it which push this molten rock upward as well. If the rock solidifies below ground, we call that an intrusive igneous rock. If the molten material makes its way to the surface and explodes out in the form of a volcano, for example, that would be a volcanic rock or an extrusive igneous rock. What's interesting to note is that the extrusive igneous rock, like this one here called a basalt, has very small crystals in it. So much so that it's really hard to see them. Whereas an intrusive igneous rock might be something like this, a granite. And you'll note that the granite has bigger crystals. You can actually see them. And the reason is that crystal size is determined by the rate of cooling. If you've got fast cooling, then the magma doesn't have time to grow big crystals in the recrystallization process. So that means the crystals are going to be small. If it's slow cooling, then crystals have a chance to actually grow. So we note that continental rock, which has a lot of granite in it, is going to be big crystals. Basaltic rock, which is fast cooling, has very small crystals. If you have super fast cooling, then you can have what's called obsidian. And obsidian is essentially a volcanic glass. And typically, if this molten material maybe hits a body of water, it's going to cool off super, super fast. And when it cools off super fast, then you don't have any opportunity for crystals to grow. It's fairly random and it becomes a piece of glass. So again, that would be a volcanic or an extrusive igneous rock. Yeah, it's really quite fascinating. You'll note too that with this granite rock, it's salt and pepper looking, whereas the basaltic rock is fairly dark. The basaltic rock is going to be iron rich. This granite rock is going to have iron, which is the dark stuff, but it's also going to have a lot of silicon dioxide or quartz in it. Now, you don't need to know that right now, but this is going to be super important later on when we talk about various activities of plate tectonic movement. So this is going to be super important. And then especially when we get to volcanism, this SiO2 is going to be hugely important if we talk about volcanoes and their strength. This will be important. So we'll get back to it later. Okay. Here's some examples of igneous rock. Again, here's granite. This one has a lot of silicon dioxide in it. It's fairly light in color. We refer to these rocks as felsic, which is feldspar and silicon rich. So again, in this particular format, we see a lot of silicon rich rock. If it was more iron rich, we would call it mafic. In this case, we call it felsic because it has a lot of silicon in it. And again, the silicon content's around 70%, so it's no joke. Here's the basaltic rock, and again, this is more mafic. It has more magnesium and iron in it. This is a nice example of a basaltic rock. And again, way more iron than silicon. Here's fast cooling. Again, basaltic, very hard to see crystals because the crystals are very small because it cools off so fast. Whereas here's coarse grain, slow cooling. And again, you see the size of these crystals are fairly substantial. For those of you who might travel to the desert quite often, if you go east of here, 29 Palms, for example, Palm Springs, Palm Desert, you'll see periodic areas of big slabs of granite rock, and the crystals are so big you can actually climb them. And if we take a look at this again, you'll notice that if you have an intrusive igneous system, over time, if this sedimentary rock can weather away and the granite root is exposed, then this is at the surface. And this is what we see with deserts east of us. We have these big slabs of granite rock that are intrusive igneous processing. And again, those crystals are absolutely huge. You can climb those things. Here's more slow cooling. This is interesting. This is a porphyritic type rock. So you've got big texture stuff in there. You've got some obsidian also. So this is sort of a strange process where you've got a mix of content in there. Here's your obsidian glass. Again, it cools off so fast that you don't see any crystalline structure. By the way, we see obsidian all over the the southwest of the United States. Arrowheads were made of obsidian glass. They can just become really fine and sharp. Spearheads were made of obsidian glass. Even hospital scalpels for a while were made of obsidian glass because you can get really fine cuts and you can have lesser scarring versus steel scalpels. So obsidian is a really interesting product, and again, it results from volcanic activity. All right, so those are our igneous rocks. Let's take a quick look at sedimentary rock. Sedimentary rocks form from sediment, which is a byproduct of weathering. About 75% of all rock outcrops on continents are sedimentary rock. Sedimentary rocks are used to construct much of Earth's history. They give clues about past environments, and we saw this when we were looking at paleoclimatology. It provides information about sediment transport, which we can talk about later, and these rocks will be the ones that contain fossils. You can't have a fossil in an igneous rock because the igneous rock has undergone a melt process. You can't have a fossil in a metamorphic rock because the metamorphic rock has undergone changes in its structure due to heat and pressure. But you can have fossils within sedimentary rock. And again, those sedimentary rocks don't undergo melt, they don't undergo extreme heat and pressure. So anything that is saved biologically in a rock, it's going to be within a sedimentary. There's other sedimentary rocks too that are extremely important economically speaking. Coal is a sedimentary rock. Petroleum and natural gas are byproducts of sedimentary processes. And then, of course, sources of iron and aluminum, like iron ores and aluminum ores, those tend to be sedimentary features as well. So sedimentary, let me put a star by it because it's pretty important stuff. So there's a lot on this board, and let me go through it relatively quickly. There are two groups of sedimentary. There's the detrital, and then there's the chemical. Detrital sedimentary rocks are classified by particle size, and the material is solid particle. And again, these are rocks that have undergone a weathering process, and the pieces of the existing rocks break up into sediments. It is these sediments that can inevitably find their way together, lithify, and then form another rock. Common sedimentary rocks that are detrital or shale, for example, this is more like a mudstone because the sediments are super small. There's sandstone, and the sediment size is sand. There's conglomerate, where you actually have pebbles, and you've got sand, and you've got mudstone all together in a conglomeration. Those would be typical detrital sedimentary rocks. Chemical sedimentary rocks, on the other hand, are derived from material that was once in solution and precipitates to form sediment. So, it's directly precipitated as a result of physical processes or through life processes like biochemical origin. Seashell is calcium carbonate, CaCO3. This is a sedimentary rock, and it is formed through biological process. Animals in the sea take calcium, take the carbon trioxide, they can meld it together into a chemical formula, and they make seashell. Whereas something like a rock salt, like I said, it's in solution, the water can evaporate, you're left with rock salt because the NaCl precipitates out, and that can make another sedimentary rock. Common rocks of the sedimentary chemical genre include limestone. Again, limestone is actually CaCO3. A lot of that is seashell. You've got a lot of microcrystalline quartz, known as chert and flint and jasper or agate. You've got evaporate, such as rock salt or gypsum. And then, of course, you have coal. All of these are common chemical sedimentary rocks. And without belaboring the point too much, here is how you define detrital. And again, it's all by the size of those little sediments. Whereas when you define chemical, it's all by the texture and how it was made. I'm not going to ask you to memorize a bunch of ways to classify sedimentary rocks. Our real goal is to understand the differences between the two. So let me give you some examples. Here's shale, and you'll notice the fossil imprint in the shale. So when we talk about fossils, it's not just talking about like, is there a bone that's buried in the ground that's a few million years old? You can have imprints as well. So here's a leaf imprint. You can have a physical foot imprint of a particular animal. And shale or mudstone is a really good houser of that kind of fossiliferous information. Here's sandstone, very typical. Then you can see that it's sandy and fine grain. Use this as sandpaper, of course. Here's a nice conglomerate. And in our conglomerate, we see pebbles, we see sand, we see fine particles all the way to big particles. This is typically going to be found in a very energetic body of water. And that makes sense because the river water has to be strong to be able to push all of these bigger, grain particles going from the big ones to the fine ones down a river to inevitably conglomerate together in what's called an alluvial fan, which we can talk about later as well. Energetic. You know what I'm saying. Okay. Here's a fossiliferous limestone. So we've got a lot of seashells here that are fossils. And here's your rock salt. Nice crystalline, squarey, cubic structure of these rock salts. Down here in San Diego, we have a really nice rock salt farm. It's down in South Bay. You've got right by the Imperial Beach area, there's this whole area which is really thin water, so the tide comes in and then the water is very salty. Then the water evaporates and it leaves the salt behind and is harvested. So there's a lot of salt that's down in that area as well. Here's sedimentary production through lithification. So let's say, for example, we've got a river that's running from our mountainous zone. And within the river, you've got maybe igneous rocks, for example. These igneous rocks are going to break up into sediment. They break up into sediment. They flow through the river. They're deposited out into the sea. What's left behind is going to give you beach sand. So the beach sand that we have in San Diego is predominantly coming from mountains. And then sediments will drop into the ocean. And then over time, they just get buried. So this burial and lithification where they cement together, that forms sedimentary rock. So a lot of our sedimentary rock is actually coming from an origination point of the mountainous zones. And our beach sand in particular is coming from these mountain zones as well. Features of sedimentary rock include a lot of strata. So again, they're buried in layers. You get bedding. In terms of fossils, you'll have traces or remains of prehistoric life. You'll get all sorts of inclusions. And what's really cool is, let me give you a prime example. If we take a look at somewhere like the Grand Canyon, it's really, really impressive. The Grand Canyon was cut by the Colorado River, and it's taken millions and millions of years for this little river to cut this canyon. Now, the canyon itself was created, at least the layers of it, by eon after eon of deposition, just like you see here. What's interesting to note If you go to the Grand Canyon, at the very top of the Grand Canyon, you'll see marine fossils. Therefore, you know that this whole area used to be underwater millions of years ago. You have beneath that a layer of vertebrate tract fossils. So you know that we're dry now. There used to be underwater, but before that it was dry because we got vertebrate animal tracks. Beneath that we have plant fossils. Beneath that we have marine fossils. Beneath that we have trilobites. Trilobites are some of the oldest fossils that we find on Earth. And then beneath that, we got information regarding single-celled organisms. It's the craziest thing. In addition to that, we have what's called an angular unconformity, and that you can see the angular unconformity here. And that tells us, geologically speaking, that back in time, there was a major geologic event, like a major earthquake, which shifted the landscape. Because again, sediments are pretty much deposited via layers, just like you see here. So if you have an angular unconformity, then that means there was a major shift in geologic activity during this period of time. So sedimentary rocks are super interesting. We get a lot of cool information from it. Just a short recommendation, if you've never been to the Grand Canyon, take the time one of these days to go. And when you go, you hopefully won't be disappointed. It is just such a marvelous sight to see, and pictures do it absolutely zero justice. All sedimentary. All right, and finally, the last type of rock, and this is where we're going to end our discussion this evening. My apologies for cutting it short, but I've got a meeting that I've got to run to, but that's okay. We're finishing our discussion of rocks. Let's take a look at metamorphic rocks. Metamorphic rocks are changed form rocks. They are produced from pre-existing igneous rocks, sedimentary rocks, or even other metamorphic rocks. Metamorphism takes place where pre-existing rock is subjected to temperatures and pressures unlike those in which it formed, and it's got to be pretty extreme. Now, there are degrees to metamorphism. You have low-grade metamorphism, mid-grade metamorphism, and high-grade metamorphism. High-grade metamorphism is generally going to give you foliated texture. And this is foliated texture here, this picture. So let's say that we've got an existing granite rock. And this granite rock is salt and pepper. You've got dark spots, which are iron. You've got the light crystals, which are quartzy. You put this rock under extreme heat and pressure, then what happens is you get differential stress. And the like minerals begin to line up. That is the foliated texture. And you see that here in this new metamorphic rock called gneiss, or gneiss, depends on how you pronounce it. And you'll note here that you've got this nice linear foliated texture. This typically occurs with high-grade metamorphism. And again, minerals become perpendicular to the compressional force. That's foliation. Non-foliated texture is going to contain equal dimensional crystals, resembles a coarse-grained igneous rock. Marble is going to be a really good example of non-foliated, and it's low-grade metamorphism. So let's take a look at some of these. So again, our rock name, maybe we've got slate, phyllite, schist, or gneiss. These are all metamorphic rocks that are foliated. This is the general texture. The grain size is very fine, going all the way to medium or coarse. This is high grade. This is low grade. These are mid grade. Slate, by the way, I wish I had an example to give you that you can touch and hold. Clean the slate. That's a true thing. And so back in the day when we had chalkboards, chalkboards were generally made of slate, and you would use limestone or talc chalk to write on it. And when you were done, you would obviously clean the slate. And so that's where that phrasing comes from. These are all foliated. Non-foliated metamorphic rocks include marble, quartzite, and anthracite. And again, these are all metamorphic rocks. And this is a really nice chart because it gives you the parent rock. Shale, mudstone, or siltstone, you metamorphosize it, it turns to slate. You take slate, you metamorphosize that some more, you get phyllite. You take phyllite, you metamorphosize it some more, you get schist. You take schist or granite rock, for example, which is igneous, you metamorphosize that some more and you get gneiss. The same game can be played with these other non-foliated metamorphic rocks. You take limestone, for example, you metamorphosize it to marble. You take quartz, you metamorphosize that, you get quartzite. You take bituminous quartz or coal and you metamorphosize that and you get anthracite. So again, this is how you get your metamorphism. It's high pressures, high temperatures. You're not melting anything though, because if you melt it, it's going to go igneous. Here's a nice appearance of gneiss. Again, really nicely foliated. Here's marble, really pretty. You get this nice crystalline structure still. And by the way, I can ask you very quickly, which do you think is more weather resistant, marble or gneiss? If you're answering gneiss, then you're right. Because gneiss is made with higher pressures and temperatures. So frankly, it's a stronger rock and is basically more stable to a certain extent. Marble weathers quite easily. And so marble headstones of the past, that's not good. If you go to a cemetery that's 100 to 200 years old, marble headstones, the RIP is weathered away. And so most headstones today, outside anyway, are going to be made of granite because it's just simply more weather resistant. All right, one quick thing. I want to really highlight the fact that one rock is the raw material for another rock. So let's say we've got our igneous rock. Let's say we've got our sedimentary rock. Let's say we've got our metamorphic rock. If you take igneous rock and if you put it under weather, you can make a sedimentary rock. If you have a metamorphic rock and if you put this under weather, you can get a sedimentary rock. If you take a sedimentary rock and you melt it, you can get an igneous rock. If you take a metamorphic rock and if you melt it, you can get an igneous rock. If you take an igneous rock and you put it under extreme heat and pressure, you can metamorphosize it. And if you take a sedimentary rock and if you put it under extreme heat and pressure, you can metamorphosize it. So one rock is absolutely the raw material for another rock. This, by the way, is the answer as to why we don't find 4.6 billion year old rock on planet Earth. It's because of the rock cycle. The second that you melt a rock, it's now day old 0. Every rock on our planet has undergone the rock cycle. It's all been regurgitated within the system. Therefore, we're not going to find 4.6 billion year old rock. That we've even found 4 billion year old rock is super impressive. That's the rock cycle. You go somewhere like the moon doesn't have plate tectonics, which we'll talk about in a second, which means it doesn't have a melt process, which means rocks there are going to be found older, right? So I gave myself away a little bit. I said, what's creating this cycle? Atmosphere obviously is affecting weathering. In terms of melt and heat and pressure, we have to turn to something called plate tectonics. Plate tectonics. And so, in our next conversation that we'll have live, I'm going to go over plate tectonics because it's important. And so, up to this point, we've talked about the interior of the Earth and what it looks like. In addition to that, we've talked about rocks and the rock cycle. The next question is, what creates the rock cycle? And the answer is going to be plate tectonics. Not only is the answer plate tectonics, But earthquakes is because of plate tectonics, mostly. Volcanoes is because of plate tectonics, mostly. And so plate tectonics becomes the key to our understanding of landform and landform evolution. I will say very quickly, with regards to earthquakes, plate tectonics mostly is the right word. And I only say mostly because if you go somewhere like the Midwest of the United States of America, every now and again you hear about an earthquake. If you know anything about geology, you know that that earthquake is not because of a plate boundary, which we'll talk about later. It's actually because of isostasy. So back in time, that whole area in North America used to be covered by ice. It no longer is. So we've essentially shaved off a weight that's been on top of the continent, but because of isostasy, the continent is rebounding. That rebounding is what can create periodic earthquakes in parts of the world where you think earthquakes shouldn't occur. So that's why I'm using the term mostly in terms of earthquakes and plate tectonics. Okay, with that said, next time you and I have a conversation, although you'll be doing this on your own as well within the class, these are the pictures that we'll be talking about. And we'll be figuring out why the world looks the way it does. All right.